What's the matter? What is matter? Suppose your class takes a field trip to a museum. During the course of the day, you see mammoth bones, sparkling crystals, hot air balloons, and an astronaut's spacesuit. All of these things are matter. As you will see, matter is anything that has mass and takes up space. Your body is matter. The air that you breathe and the water that you drink are also matter. Matter makes up the materials around you. However, not everything is matter. Light and sound, for example, are not matter. Light does not take up space or have mass in the same way that a table does. Although air is matter, a sound traveling through air is not. What is mass? You cannot always tell how much matter is in an object simply by observing the object's size, but you can measure the object's mass. Mass describes the amount of matter in an object. Compare the two balloons at the right. The digital scales show that the balloon filled with compressed air has a greater mass than the other balloon. This is because the compressed air adds mass to the balloon. Air may seem to be made of nothing, but it has mass. The readings on the scale are in grams. A gram is the unit of mass you will use most often in science class. Objects that are the same size can be made up of different amounts of matter. For example, a large sponge is about the same size as a brick, but the brick contains more matter. Therefore, the brick has a greater mass than the sponge. And let's take a look at our balloons. The readings on these digital scales show that all matter, even air, has mass. So here's our balloon without air in it. It's at 0.005 or 5/1000ths of a gram. And then here's a balloon filled up with air. It's at 0.010 or 10/1000ths of a gram. So this has more mass. How much does mass differ from weight? The words weight and mass are often used as though they mean the same thing, but they do not. Weight is a measure of the gravitational force on an object. Gravitational force keeps objects on Earth from floating into space. The gravitational force between an object and Earth depends partly on the object's mass. The greater that the mass of an object is, the greater the gravitational force on the object will be, and the greater the object's weight will be. An object's weight can change depending on the object's location. For example, you would weigh less on the moon than you do on Earth because the moon has less mass and therefore exerts less gravitational force than Earth does. However, you would have the same mass in both places. An object's mass does not change unless the amount of matter in an object changes. So the weight of this dachshund on the moon is about 1/6 of its weight on Earth. How are mass and weight measured? Mass is often measured by using a triple beam balance such as the one shown above. The balance compares an object's mass to known standards of mass called countermasses. The countermasses slide across each of the three beams. When the countermasses balance the mass of the object in the balance pan, the pointer will rest at 0. Then the mass can be read from the position of the countermasses on the beams. Weight is measured with devices such as the spring scale shown at the left. The spring measures the force between the mass in the pan and Earth. The more mass of the object placed in the pan, the more forceful is the attraction between it and Earth, and the more the spring will stretch. Greater stretch means greater weight. Because weight is a measure of gravitational force, it is given in units of force. You probably are most familiar with weight given in pounds, like the units shown on a scale. The standard scientific unit for weight, however, is the Newton. A 100-gram mass weighs approximately 1 Newton on Earth. 1 Newton is about 1/4 of a pound. So here is a triple beam balance that can be used to measure the mass of small objects such as this geode fragment. And this is the spring scale, which gives weight in pounds.